We can change the path of a small asteroid. Power grids rely on quiet skies. Global shipping follows predictable routes. Insurance models assume yesterday looks like tomorrow. A change that normally takes centuries can be made to happen over years. The first changes are subtle, the later ones are not, and by the end, the world still functions, just differently. It is possible with a large, thin mirror called a solar sail. This is not science fiction. It is engineering grounded in the fundamental laws of physics. Light itself seems weightless, but it has a tiny, persistent push. Over time, the accumulated push from countless photons can move a mountain of rock in space. A tiny change, introduced early enough, can lead to a massive deviation from the original path. A miss of thousands of kilometers can begin with a nudge of just a few millimeters per second. A quiet, clean, continuous method of propulsion. We use fundamental forces to protect our home. To understand the plan, we must first appreciate the scale. An asteroid is a rock in space, a remnant from the birth of our solar system. Some are small, the size of a car or a house. Others stretch for kilometers, vast enough to hold a city. A small asteroid, a few tens of meters wide, could still release the energy of a powerful nuclear bomb if it entered our atmosphere. A large one could trigger a global catastrophe. The force we can apply is minuscule. The main idea is to apply this steady, tiny force for a very long time. Think of it like moving a ship with a gentle wind. Not a puff, but a constant breeze across days. In space, our wind is the stream of photons from the sun. As long as the sail faces the sun, the push is there, minute by minute, year after year. This is how a small push can make a big difference. A solar sail is simple in concept. A very thin, reflective sheet stretched on booms. When a photon bounces off, it transfers a tiny amount of momentum, action, and reaction, precisely as Newton described. The push is steady, quiet, wonderfully efficient. No fuel is burned, no propellant is consumed. Rockets give a powerful shove, then stop. A sail keeps accelerating as long as it is in sunlight. That means lighter spacecraft and cheaper launches. We trade raw power for time. Perfect when warnings arrive years in advance. Use the very light that illuminates the asteroid to steer it. A calm, measured, deeply rational response. There are two main concepts: direct attachment and a standoff gravity tractor. Direct attachment means anchoring a large sail assembly to the asteroid itself, then unfurling hundreds of meters of reflective film. Designs range from low-velocity harpoons to multiple anchors like tent pegs, to a full net harness to spread the load. Everything must be gentle. Rubble piles are weak, spin in odd ways, and dust can dull a sail. The standoff approach never touches the rock. The sail pushes the craft. The craft's gravity tugs the asteroid. A delicate dance. Ion thrusters keep precise position. The physics is clean, the trajectory predictable, and the process very slow. At Earth's distance, sunlight pressure is about 9 micronewtons per square meter, 1/100th the weight of a sugar grain on a 1 square meter sail. Scale to a 1 kilometer sail and you get around 9 newtons, about the force to lift a gallon of milk. Moving a mountain with a milk jug's lift sounds absurd, until you remember, space has no friction and you have years. Sails use ultra-thin films, like Mylar or CP1 with aluminum just atoms thick. Strong enough to unfurl, light enough to fly, they must endure micrometeoroids and relentless radiation without tearing. Sunlight fades with distance. Near Mars, the push is roughly half. Near Venus, nearly double. In 2010, JAXA's Icaros deployed a 14-meter sail and controlled flight by sunlight pressure, flying past Venus. In 2019, the Planetary Society's Light Sail 2, loaf of bread-sized, raised its orbit with a 32 square meter sail. These missions solved packing, deployment, and pointing, moving solar sailing from theory to proven flight hardware. Next comes a demonstration at a tiny safe asteroid to measure a controlled, predictable nudge. Miscalculations are the first danger. Mass, composition, or initial trajectory errors can turn a near miss into a problem. Aggressive anchoring can fragment the target. A debris cloud is harder to track than a single rock. Even intact, a new wobble can defeat precise thrusting. Dual-use risk demands international law, safeguards, and shared governance. And small changes today ripple through decades of gravitational interactions. Hence, slow, gentle, reversible methods, with exhaustive simulations and staged demonstrations. Planetary defense is global insurance. Impacts have happened. They will again. Deflection capability protects cities, ecosystems, and lives. Asteroids are time capsules from the solar system's dawn, scientific treasure. Some hold iron, nickel, cobalt, platinum group metals. Others hold water for propellant. Access unlocks an in-space economy. Safety, science, and resources reinforce each other. Funding, knowledge, and capability aligned. Ultimately, this endeavor is a human one. A faint point of light shifts by centimeters per second, enough to matter years later. No explosion, no spectacle, just competence and patience. Detection, tracking, and planning are inherently international. We will need laws, transparency, and clear authority for deflection missions. Explain risks and benefits plainly. Bring the public along. How do we best attach a sail to a loose rubble pile? How large must a sail be to steer a stadium-sized rock on schedule? What safeguards ensure this power is used only for peace? These questions will occupy the next generation, across labs, control rooms, and courts. With decades of warning, slow sunlight pushes yield predictable, decisive outcomes. By the end, the world still functions, just differently, with a practiced, rehearsed planetary defense. Capability begets capability. Depots, construction, and science flourish in tandem with safety. A gentle nudge to save a world, trading urgency for foresight, fuel for light, and spectacle for reliability. We can change the path of a small asteroid. The journey has begun, but the destination is still being charted. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.